So, so in the core of the horizontal branch star, you're fusing helium into carbon. Well, you can't keep doing that forever because the helium will keep fusing, but as the helium fuses into carbon, then what happens is that the helium will eventually run out, just like the hydrogen ran out when it was a main sequence star. Now, the problem is that helium fusion is only about 10% as efficient as hydrogen fusion. So a star like the sun could last 10 or 12 billion years fusing hydrogen into helium, but only about a billion years or so fusing helium into carbon. And so it's going to run out a lot quicker. And so when it does, then the core once again quits fusing. And so once again, you get a core that's not fusing, but now it starts shrinking, and surrounding it is a shell of helium that fuses into carbon, and that surrounding that's a shell of hydrogen fusing into helium, and surrounding that is all the rest of the star that's still hydrogen for the most part. And so the outer parts are always still hydrogen. And so it does the same thing it was doing when it swelled up the first time to be a red giant, except now we have two shells fusing, not just one. And so it swells up to be a red giant again, except now it's a bigger red giant. So at that point, the diameter of the sun swells up to be 1 AU, and then it swells up even more, so the radius is 1 AU, so the diameter is almost 2 AU. That means the outer edge of the sun comes out all the way to where Earth is. And so that, a lot of books would then say that Mercury, Venus, and Earth are then swallowed. It turns out a little more complicated than that. As the temperature increases in the core, a little bit of that carbon will grab some stray heliums and will fuse into oxygen. You put a helium and a carbon together, you get oxygen. And so what happens is the core is going to be mostly carbon, but with some oxygen produced also. This is one reason that oxygen and carbon are some of the common things that you find in the universe other than hydrogen and helium, is they are byproducts of this fusion process inside there. A little bit of incomplete fusion, you get a little bit of nitrogen, you get some other sort of things in there, but these are the primary things. Okay. So the second red giant, the outer edge of the sun, comes out practically to Earth's orbit. Deep in the middle are these tiny little cores. The carbon oxygen core is only about the size of the Earth, and you have these shells surrounding it. And so all those shells are smaller than the sun currently is. The outer edge of the sun swells up. Now, that doesn't mean the mass of the sun increases. In fact, the mass has not changed appreciably in all the expanding and contracting. You're turning a little bit of mass into energy. The biggest thing that happens, though, as a red giant, though, is that the outer parts of the sun are now very, very far away from the middle, and so gravity is weaker. And at that point, just the light pressure and the heat and other sort of things just cause the outer parts of the sun, atoms and molecules, to start drifting away. And so it's kind of like the solar wind, except the solar wind on steroids. It's much, much more active, and so you end up with a huge amount of mass leaving. We call that the red giant wind. Slower stuff coming away from it than the current solar wind coming away from the sun right now. Depending on the star, 10% of the mass over the time it's a red giant here or a second red giant, 10% of the mass can leave, up to 80% of the mass. So a huge fraction of the mass can leave. The sun will probably lose maybe a third of its mass or more as this red giant went. Between a quarter and a third of its mass might leave. Somewhat larger stars push away more of their mass. Somewhat smaller stars push away less. So a star that's originally half the mass of the sun might only lose 10% of its mass. A star that's maybe 5 or 6 times the mass of the sun can lose 3/4 of its mass at that point. Uh, the dying star TT Cygni is a red giant that's lost a bunch of mass, which is expanding outwards in a shell around it, and so that's some of the stuff that's been lost. And so this kind of artist's impression of what the sun would look like from Pluto at this point as a red giant, and so that's going to be the red giant. Okay. So the red giants, because they've expanded so much, the outer edges are far away. You have different layers inside of them that are different temperatures and different pressures. They become very, very unstable, and they tend to pulsate. That's where a lot of these pulsating red giants come from. That's what Cepheid variables are Lyra variables, the long period variables, semi-regular variables like Betelgeuse. All these things are these red giants that are unstable out there, and so they pulsating. Now, the sun, at the end of its main sequence life, it's going to be between 10 and 12 billion years. So in my slide here, I say about 11 gigayears. A giga is a billion. So about 11 billion years old. The sun would have been swelled up a little bit. It'd be about twice as bright as it currently is, about 1.6 times bigger. In about a billion years, it's going to swell up to be a red giant. It's going to be the outer edge of it is going to swell up to about where Venus is, and it's going to be over 2,000 times brighter. But it would have lost about 28% of its mass. And so that means that, while a lot of books say that Venus orbits at about, 0.7 something AU, it gets swallowed. Venus, if it survives, would have moved outwards because there's less mass, less gravity, and Earth would have moved outwards. Earth would have moved out to almost where Mars is now, and Venus would have moved out to where Earth is. Now, that doesn't mean Earth is going to still be nice, because the sun is about 2,000 times brighter, so moving out a little bit, cuts the energy to the sun only by a tiny fraction. Venus has moved out to where Earth is. Now, if it loses mass faster than it swells up, Venus is saved, sort of. If it loses mass slower than it swells up, Venus gets absorbed by the sun. So it just depends on how quickly it loses mass. I say sort of because it's still going to be so close to the sun, this really bright sun right here, that Venus is going to be basically molten. In fact, the wind out here is going to strip Venus of its atmosphere and probably the crust also. So the wind and the heat will probably strip Earth of its atmosphere. Okay, so even though it's there, it's not very nice. After the helium flash for about a billion years, the sun shrinks. The sun's going to be a little bit smaller. It's going to be only about 41 times brighter than it currently is. Still, Earth's going to be in pretty bad shape. Over the next 110 million years, it gradually gets bigger and brighter, and then expands to be a red giant the second time. It takes only about 20 million years for that. Which, long by human terms, but very fast compared to how long the sun's been living. At that point, the outer edge of it will expand to like almost an AU. The sun would have lost about half of its mass if Venus survives, and it's highly doubtful that it would really survive, other than maybe just as an iron core at this point. It's going to swell up. It's going to move outwards. Earth will move out a little bit, but Earth will probably be stripped of its crust and maybe mantle also by the red giant wind. Core instabilities, the hydrogen shells, hydrogen helium burning shells, they speed up, they slow down. The sun's going to start pulsating. It gets bigger and smaller, bigger and smaller. Every time it gets big and then small, some stuff just keeps going. And finally, after about 4 pulses, the outer layer detaches and blows off into space. And so it's going to pulsate a little bit. The outer layer blows off into space, and that's going to leave behind a cloud of expanding gas surrounding what's left of the star. And that cloud of expanding gas is a planetary nebula. And so at this point, the core is this tiny little thing that's only about half the mass of the sun. It's hot, over 120,000 Kelvin, giving off a whole bunch of UV, which causes that cloud of gas to fluoresce and glow out there. And so it actually excites it, not so much fluorescing, but it excites it and it glows. And so if Earth survives, it's going to be at about 1.8 AU from the sun at this point, and that cloud of gas will be pretty. And so William Herschel, when he looked at these things in the sky, he saw these round clouds of gas and called it a planetary nebula. And so that's one of these remnants left over from after the sun dies. The thing in the middle is going to be what's left of the core. It's going to be hot. It's going to be very small. It's going to be mostly carbon and a little bit of oxygen. Talk more about that later.